Okay, so let's get rolling. I just about have the midterms done. I have two questions left. So the good news is for you, I won't give you an assignment over the weekend. So you get a little bit of a breather. I know you've had a lot of stuff over the last week, and you probably have midterms next week too. So that'll give me a chance to catch up. I meant to finish the grading last night. My back was killing me, and I figured it wasn't going to do you any favors, me grading in a bad mood. So, um, I'll get them done this afternoon while my wife's at her cancer treatment, and I have like a 2 hour window to burn. So I apologize for that. Okay, so let's see if I can figure out these last two. We were going through the midterm last class, and we're really trying to emphasize this idea of breaking problems down into tiny, tiny, tiny steps. Okay, and I think this next one really exaggerates that problem. If you get too stuck into trying to solve the whole problem, you're going to kind of be paralyzed and not even know where to start. I know many of you have probably been in that situation where you read a question, you're staring at the screen, and you're like, I don't even know what the first thing to do is. Normal, normal for beginning programmers. All right. So you have to just start training yourself to break it down as what is the smallest little step that I can solve that puts me in a direction towards this solution. All right. And once you get used to doing that, it'll start going quicker. All right. So this next question, write a function that takes an integer as an input and returns the greatest difference between any two digits of that number. So let's just kind of look real quick just to make sure we're fully understanding the question. So if we have the integer 123, we want to find out, and it's asking for us to return the greatest difference, correct? Returns the greatest difference between any two digits in that number. Shut this. All right, so first thing we're going to need to do is turn it into a string. We need it in a string format in order to even compare anything. Otherwise, we can't walk the int by individual digits. Make some sense? All right, let's write just that one little piece. Go back into our code here. I've prototyped it, takes an int as a parameter, and it returns the greatest difference between any of those digits. All right, so why don't we go ahead and just create a string called num and set that equal to toString of n. Good there? So now we have a variable called num, and it holds whatever number n held, but holds it as a string. So we've accomplished the step of going from there to there. Everybody good with that? All right. So now what we want to accomplish here for this particular question, if we just solve it as a human being, I want to find out what is the greatest difference between any of these digits. So 1 to 2 has a difference of 1. 1 to 3 has a difference of 2. 2 to 1 has a difference of 1. 2 to 3 has a difference of 1. 3 to 1 has a difference of 2. 3 to 2 has a difference of 1. So when all was said and done, the greatest gap was 2, right? So this guy should return a 2. So how did we accomplish that? Well, we went through every single character in this string, right? As a starting point, I went from 1 to 2 to 3. Okay, so let's write that piece. For int I is equal to 0. I is less than num dot length. That's the number of digits in our number because we now have it in a string. I plus plus. All right, so now we have our index I that allows us to compare every, that allows us to work with every digit in that string. All right, so now I is currently 0. So I'm looking at the char 1. Now it's probably going to be beneficial for us to be able to turn the char 1 into the number 1, correct? Because we're going to have to be doing some math. what's the distance between this number and this number when I actually have chars? Make some sense? In actuality, in this particular case, do we need to convert them to uh, two numbers? Why not? We expect them to all be values between 0 and 9, right? Legal digits in the decimal base. We know those guys are on the ASCII table, and we know they're right next to each other in the ASCII table. So the difference between the ASCII value of any of those two chars is going to be the same. Like the ASCII value of 0 to 1 is a difference of 1 because they're right next to each other. Now, having said that, that's kind of an under the hood tricky type thing, right? Anytime you're having to deal with ASCII values, like, I don't know about that. You feel like you got to start pulling out charts to confirm your suspicions that all the digits are next to each other, just like all the letters are next to each other, because that really only works on letters and the digits, because punctuation and stuff isn't in any special order or anything like that. But for us here, that kind of feels like a weird solution. So why don't we go ahead and write a quick little function? We may even already have it written from before, but write a function that I could pass a char to, a char representing 0 to 9, and it gives me back the number, just so I can do math with it. Make sense? All right. Oh, I lose somebody. Okay. So let's say, did I already write that one? Char, here's char to number. Let's see what that guy looks like. Char to number takes in a char as a parameter. We created a string with all the numbers in it. We looped through. We asked ourselves, is the char I'm currently looking at equal to the char that I was looking for? If it is, return where I found it. 0 is at position 0. 1 is at position 1. 2 is at position 2, so on and so forth. All right, so we already have this little helper function that converts some char to a number. All right, so let's go back to our find greatest difference thing here. So for every single number in our string, for instance, I'm currently looking at a 0. What do I want to do? I want to compare it to every other number in the string and find what the distance is between the digits, right? Well, if I want to go through every value in a string, that's a for loop that goes through every value in the string. So I'm going to put another for loop in here. We'll call this int j is equal to 0. Keep going as long as j is less than num.length. J++, just another counter. All right. So our outer loop is going to go through every character in the string. So we're currently looking at that character. Our inner loop is going to go through every character in the string. So we're currently looking at that character. And we want to find the difference, the distance between two numbers, as long as we're not comparing it to ourselves. We could even compare it to ourselves because that would just be 0, right? We don't even have to make a special case for it. That's not going to be the winner, right? But if you wanted to ask a question, only try to compare if I and J are different numbers. That way we're not comparing to ourselves for no good reason. So we'll ask the question, if I is not equal to J. If I'm not looking at the same char, let's not bother. If I am looking at the same char, let's not bother doing any math. But if I'm looking at two different characters, let's find the distance between those characters. So we'll call this int diff. And what we're going to do is we're going to say, what do we call it? Char to number. And we're going to pass it num at bucket I. And that's going to give us a number, right? And then we're going to subtract from that char to number num at bucket J. All right. So now diff holds the distance between whatever digit was stored in number at bucket I, num at bucket I, and whatever digit was stored in num at bucket J. And we know I and J are not the same as each other because we wouldn't be in this if statement if they were. All right. So now it's possible that diff is currently a negative number, right? So we really want the absolute value of that guy. If we're really going to compare differences, we don't care that it's -1 or -2. We just want to not throw out a -2 when the current winner is 1. All right. So how can we take the absolute value of diff? Well, what does the absolute value mean? Disregard sign. So if it's a negative number, make it a positive one. What if it's already a positive number? Leave it alone. So if diff is less than 0, diff equals diff times -1. So after this line right here, diff is a positive number and it represents the distance between the value stored in num at bucket I and the value stored in num at bucket J. Right? So we want to ultimately return the greatest difference. So we need to somehow keep track of our current winner. So let's go up here and say int cur largest difference. And let's start that guy off at a -1. That way we'll replace it the very first time through. We will definitely have a distance between the first two values we compare of something other than -1. This does kind of assume we have at least a 2-digit number. We could ask the question if the length of the string is 1, then just return question mark or some error or something like that. So we're assuming it has at least 2 digits in it. All right, so once we have diff in a guaranteed positive format, we'll ask the question, if diff is greater than cur, what do I call it, cur largest difference, then we'll say cur largest difference gets replaced with whatever diff currently is. All right. But we're only going to do that if I and J are different values. So for every value, bucket I in num, we're going to compare it against every value, bucket J in num, except when I and J are the same. So we're going to compare to every other character in there. We'll make sure that the difference between those two positions is always a positive number. And then we'll find out, is the difference we just found larger than our previous biggest difference? If it is, replace the previous biggest difference with the new one. When all is said and done, we will return cur largest difference, which should hold our final pretty much all fits there. Should hold our final biggest number, biggest difference between those. Make some sense? Now, when you first look at that problem feels difficult, right? So notice what was the very first thing we did? We went and effectively drew a picture. Let's make sure we visually understand what we're being asked to do here. I promise you, you will not be able to solve a problem if you don't understand the problem you're being asked to solve, right? And obviously, this was one of the questions that was heavily missed on the exam, right? It was a tough one, tough question. But hopefully you see it was made up of a whole bunch of little easy parts. All right, but you just had to stumble upon the easy parts. That's the connection we're trying to make. This goes back to first day of class when I said, why is programming hard? It's not because this syntax is hard. Everyone in here right now can read what I've written here. And even if you feel like you couldn't have written it yourself, you didn't know what the next line to write was, when you see these lines, you can tell me what this line is doing. You can tell me what this line is doing. You can tell me what each of these lines is accomplishing in and of itself, correct? So it's not that the syntax is hard. That's not the problem. You can read C++ syntax already. So in 8 weeks, you've gone from C++ illiterate to being fluent in reading C++ syntax. It's the problem solving. Human beings are so good at solving problems, we have trouble articulating how we solve them. That's what every single one of you that are finding this difficult are running into. You're so good at solving problems that you can't slow yourself down to break the problems into little tiny steps. You don't have the patience. This is training you on the patience. All right. Hence, put in the reps. All right. So, questions about this one? All right. And then what was the last question? I'm going to go to a new Blackboard window because I'm not sure if I have grades up on the other tab there. I don't think I do, but prefer not to have that on recording. I suppose I could have just asked somebody to tell me what the last question was, but that's okay. Yeah, I'll just copy it. Oh, I'm still working in a browser, right? Yep. All right. Oop, oop. Oh, this is the bit shift one or the distance shift one. All right. So write a function that takes a string as an integer, n. Okay, so string and an integer n. So we're going to have some word and some number as input, and then shifts all the characters in this string by n positions in the ASCII table. So for example, shifting a by 1 becomes a b. If shifting goes past a lowercase z, it should wrap back around to an a. Okay? So we're only operating within the alphabet. Now, you could always ask a question here of, am I even looking at a character? If I'm not looking at a character, I'm not looking at something A through Z, just ignore it and keep it. You could certainly do that because this is implying we're only dealing with the letters, in fact, specifically lowercase letters here. All right, so what are we returning in the end? We're returning a string, a new string that it has all of the letters modified, right? So this guy's going to return a string. It's going to call rotate n. That's what I called it. We'll take this guy string s and then int n. Oh, I didn't need to implement that yet. But we can fix that right here. And then we'll go implement it right here. Go. Give us some spaces so it's up higher on the screen. All right. So we need to go through every. Go ahead.
So when you have functions and stuff, why is the like after the string or the bool or the integer, why is the like the first like word not capitalized, but then everything else like is?
You mean this thing right here?
Yeah.
The R. You're asking why is R not capitalized?
Yeah.
I can make it capitalized. Nothing. Yeah, it's perfectly legal. This is more naming convention. typically when you name functions or you name variables, common best practices is to use something called camel case, which usually is starting it off with a lowercase letter. So rotate n, the n is capitalized. If we wanted to kind of almost spell out a sentence, so you might say rotate by n letters or something like that. You would kind of stand out more. But if you want to start it with a capital letter, you can.
Okay.
The antithesis to that, and the reason why I'd encourage the lowercase letter, it's common, it's kind of best practices anyways, but when we start dealing with classes, writing our own objects here, maybe today or Tuesday, that's what we're going into next, is writing our own objects. Classes are almost always, again, it's not a rule, but convention is a class name when you write your own object is always capitalized. So that allows you to at a glance know, am I looking at the name of an object or am I looking at a function or a variable name? Just at a quick glance. And I would say 99% of the time you can trust that, but you can name your variables and your functions and your classes outside of like putting spaces and stuff in there. You can name them however you want. I probably even made the joke last class or the class before that. It's for a long time, kind of the inside joke has been that, you know, programmers for job security write code that nobody else can read. I'm not sure if that's necessarily true anymore, but I think you just get fired if you, because our projects are so large now, for the most part, that you're not the only programmer working on the project. You're one of a team of 12 working on a different aspect of a project with a project manager who's kind of the quarterback saying, you write this part, you write this part, you write this part, and your part has to connect to their part. And this is how they link up. So somebody else is kind of telling you what to do. And if you start coming back with all your variables, you know, named after chipmunks or something like that for no good reason, you might get a chuckle, but all right. So we want to go through every character in S, right? So let's just kind of let's throw this into Keynote again. So let's say I have the string hello, and I want to rotate this 3 positions, for example. Let me lowercase it since that's what our example assumes they're all lowercase. All right, so I need to go through, and just for helpful sake here, there's our alphabet. So when I'm rebuilding my string, I'm going to be building up in an empty string. When I hit an H, is an H a lowercase letter? Is it between A and Z? It is. I want to take my H and I want to make it 1, 2, 3. Okay. Add 3 to it. Okay. So that's going to become a K. So this guy would be a K. An E, 1, 2, 3 is an H. An L, 1, 2, 3 is an O. And an O, 1, 2, 3 is an R. So for this particular one, we should get KHOOR. All right. Now, what if we had a Z on the end there? So now we go to the Z and we bump off the end, right? So Z plus 3 is going to be some value. So really, we want to go 1, 2, 3. We want a Z to become a C. We want it to wrap around the alphabet. Make sense? Okay. So we understand the problem we're trying to solve now. And if we're dealing with anything that is not found in there, we're just going to leave it alone. That's a reasonable enough approach to this. Just pretend like I don't want to do anything with that. All right. So we're going to go through every character in our string. Got our stock for loop for doing that. For int I is equal to 0. I is less than s dot length. I plus plus. Okay. So now we're going to be building up our answer inside of another string. So we're going to have to remember something up here. Maybe we'll say string answer, start off as the empty string. Now I want to ask a question. If the character I'm currently looking at, which is s at bucket I, if that character is a letter in the alphabet, that means it's somewhere between including lowercase a and lowercase z. So if s at bucket I is greater than or equal to an a, and s at bucket I is less than or equal to a z. If it's a lowercase letter, we want to do some stuff to it. We put a little comment, rotate the letter. Else, if it's not a letter, let's just keep it as is. So we'll say answer is equal to answer concatenated with s at bucket I. After we're done with our for loop, we'll return answer. So after we've gone through every single character and we've done what we're supposed to do to it, anything that's a letter, we're going to rotate. Haven't written that part yet, but threw a nice little comment in there reminding us we got to write that. Or anything that's not a letter, we just leave alone and tack it onto our answer. When all is said and done, we're going to return our answer. So that's our structure for this one, where the actual real logic, the part that you need to actually think through for this problem, is going to live right there, right? Okay, so we want to now rotate it n spots. So how are we going to do that? Well, we can find where n is in the alphabet. So for instance, here I have the alphabet. And let's just write a I'm going to write a helper little function. Did we already write one for this? Words. You don't really need one for this one, but I'm going to do it anyways because it's going to be helpful in some other stuff. All right, so I'm going to have a function that returns an int. It's going to be called index of. It'll take a string s and a character c. And what this guy is going to do is it's going to tell me what is the first location inside of S where we find whatever character C holds. And we're going to say it's going to give me a -1 if it doesn't find it. Now step back for a second and ask yourself, is that a tool that might be handy sometimes? Think about like going to shopping at Home Depot. If you buy a Phillips head screwdriver for some job you're working on right now, might that screwdriver be helpful in some other future jobs? Yeah, that's a multi-use tool, right? Same thing here. Might it be reasonable for us to be interested in a lot of different problems to find out where some character lives in some string? That allows us to find out if this string contains that character, for instance, when we're searching for vowels. That allows us to determine just the location of a character. If we want to know where in this string a certain character first occurred, maybe it's bucket 3, maybe it's bucket 5, whatever it is. This is kind of like a screwdriver, right? We can write this once, put it into our library somewhere and kind of keep it. It's not a hard one to write, so we can always just write it again whenever we need to. But I'm kind of throwing it out there as kind of our almost like bread and butter tools, things you need to have in your kitchen to do your general purpose cooking, right? Got to have, forks and knives and different things to just accomplish almost anything you want in the kitchen, but you don't necessarily need one of the fancy gadgets you see on TV that does 4 things at once for you. Those are power tools. You might want it, but you only have room for so much. So let's go and write index of. So index of is going to take some string as a parameter. I'll put a little comment before this. So it's going to say returns the first location in S where C is found, or -1 if it's not there. That's what that guy's going to do. All right, pretty straightforward. We'll have our normal loop for int I is equal to 0. I is less than S dot length. I plus plus. If S at bucket I is equivalent to the character we're looking for, return I. Remind me, what does return do? Ends the function. Return's real purpose is it makes the function die immediately. It then can optionally return a value. In this case, we are expecting it to return a value. We've advertised it's going to return an int, so this guy will return a value with it. But a super, super, super important power tool for us is to remember that the return keyword ends a function. So if you are ever in the middle of writing something, in the middle of a function, and you want to get out of this function immediately, do not pass go, do not collect $200. You want to return. Make sense? All right. Hopefully you're starting to see that we're throwing puzzle pieces into our computer programming problem solving, things that you've already built over the years for your human problem solving, right? We all have our own little patterns for doing things, and some people do one thing one way, and other people might say, well, that's kind of a weird way of doing it, but it's your way of doing it. It's your process, right? So we now have this little tool to help us do something. So we'll go back to rotate n. If we're in this if statement, that means we are looking at a character. So I'm going to go ahead and find out where is the location of that character in the alphabet. Now you could do this in a shorter way, but I'm going to kind of spell it out because I'm trying to really emphasize this idea of baby steps. Okay. So we're going to call int location in alphabet. And this guy is going to equal index of, I'll give it the alphabet, and I'll give it the current character we're looking at. Tell me where you found that character, whatever that guy is, inside of this string. Make sense? So now I have a location. So let's assume that I was dealing with an H. 0, 1, 2, 3, 4, 5, 6, 7. So I'm going to get a 7 out of this. So if I was dealing with an H and I passed the alphabet to index of, and I passed the letter H, it's going to give me back a 7. That's where I found it. All right. We're supposed to rotate this guy by n. So we're going to say int new location in alphabet is going to be loc in alphabet plus n. Go with that? Now, we do have a problem potentially. With H, we won't, unless n was really big. But if with H in our example of 3, this won't be a problem, but we still want to think about the problem. What if I've walked off the end of the alphabet? How many characters are in the alphabet? 26, right? What are the legal positions in the alphabet? In that string, what are the legal buckets of that string? 0 to 25? Because we have 26 total letters, and they're taking up position 0 through 25. All right. So now we could ask if, what do I call it? New location in alphabet, if that is greater than 25. if I've gone too far in the alphabet, I actually want to, so let's say I was Z. So I was at number 25. And then I added 3 to it. Now I'm at 28. 25 plus 3 is 28. I asked myself, is 28 greater than 25? It is. So what do I have to do? I have to start off at 0 and add to it the difference between new location and the last legal bucket. Make sense? So we are off the end of the alphabet. So wrap. So if we're in this if statement, we're going to say new location in alphabet is equal to 0 plus new location in alphabet minus, you could say, minus 25. We'll just hard code it since we know we're dealing with the alphabet here. So if we were dealing with a Z, Z is in bucket 25. 25 plus 3 is 28. Is 28 greater than 25? It is. So we're going to take the new location, which is 28. We'll subtract from it 25, and that's going to give us a 3, and we'll add that to 0. You don't actually have to do the 0 plus, but we were spelling it out here. And that will get us to the 0, 1, 2. But we don't want bucket 2. We want bucket 3. From Z, we have 1, 2, 3 onto there. So new location in alphabet was 28. We got a 3, 0, 1, 2. So we're going to say minus 1. That'll tell us the position in our string where that new letter should be. So bucket 25 plus 3 is 28. 28 minus 25 is 3. Minus 1 for 0 base index gets us the position we really want here. So now what we'll do is we want to get the letter at that position. So I'm just going to quickly here say string alphabet. I'm going to remember that since we're going to have to use the alphabet a couple different times here, right? So we're using the alphabet there. We could replace this with alphabet dot length minus 1. We could replace this with alphabet dot length minus 1. But when we get to this line right here, we know the location in our alphabet where the newly mapped letter should be. So we're going to say answer is equal to answer concatenated with alphabet at bucket new location in alphabet. Our answers are running total. Because we're looking at a lowercase letter here, we need to map it. Go ahead and give ourselves the whole alphabet to work with. Find out where the current lowercase character lives in the alphabet. Add however much we're trying to rotate to that. If that number has gone off the end of the alphabet, make it wrap. When we get to this line here, whether we had to make it wrap or not, new location in alphabet is where the next character should be. That's the mapped character. So we'll go ahead and get the character that lives at that position in our alphabet and tack it on to answer. When all is said and done, return answer. Make some sense? Now, as we walked through that one step at a time, were there any of those parts, individual parts, that were overly difficult? But putting it all together can be frustrating because as human beings, we tend to problem solve the larger picture. We're used to solving the bigger problem. So we have to train ourselves to break a problem down to tiny steps. What we've just done here in the last 5 minutes is the key to coding. Break problems down to small steps, because every single one of you in here can understand this as we walk through it, step by step by step by step. But many of you are currently going to struggle putting all those steps together to get you to a final close to correct answer. And that's where we're trying to get you. By the end of 200, you will be a lot better at doing that than you are right now. You're not going to be great. You'll be better. By the end of 250, the expectation is you're going to be even better at doing that. And what'll be interesting is by the end of 250, the next course, you'll look back to the things you found difficult in here and like, oh, well, that's not hard. But you'll have a whole new set of hard stuff that you'll find difficult. And before you know it, you're going to be a general purpose programmer, and this stuff isn't difficult. Outside of little bugs here and there, missing semicolon, you forgot to subtract one and you're one off on your mapping, things that are logic type errors that you could figure out through some debugging, right? So that's another skill you're going to run into, is the debugging skill. And most of you are spending substantial amounts of your time right now debugging because you're getting 4 million errors. All right. So the best advice I can give you with the debugging is when you get an error, the very first thing you need to do is read what the error says. Because too often what happens is, especially as you've been working on your homework for 3 hours, you're burned out and you have 500 errors. One error is just like the next one. You end up just randomly changing code until it gives you less errors. And what you don't want to do is you don't want to have a final product where like, okay, well, it works, but I don't know why. I've just tried every permutation of this thing until I solved the Rubik's Cube somehow. All right. Because then you haven't gained anything. All right. So questions on any of that stuff? So I'll go ahead and grab this link. Oh. We might talk about you in that channel. We shouldn't. All right. And it's possible I might have a couple of small bugs in there since I didn't test any of that stuff, but give it a quick run. So here's expected, comma, blah, blah before int. So this is main line 109. So 109 right here. What did I forget? I forgot the semicolon at the end alphabet there. Hit run again. Redefinition of find greatest difference. Remember we wrote that twice. I started writing at the end of class last time, and I started over today, so we don't need to redefine that function. S was not declared in this scope. I was working with a string called sentence here, and I was talking about it as if its name was S. So there's sentence. And there we go. That's all of the syntax errors. The thing it's complaining about right now, control reaches the end of a non-void statement. This is for the index of. So this is line 97. It's because we knew that it was going to return a value, but potentially the way we wrote it, since we were returning inside the loop. So let's go to line 97 here. We've advertised we're going to return an int, yet we only conditionally return a value here. Even though we know the way we're going to use this function, it's always going to return a value. So we can come down here. Remember I said return -1 if you didn't find it. So we'll return -1 there. That's our way of saying I couldn't find the character you were looking for. Same thing, control reaches the ends. This is 176. Roll down to 176. Going to be the exact same problem again. Char to number. We're inside here. We know that because of the way we're going to use this, we will definitely get in that if statement, but C++ doesn't know that. So we can come down here and just return a -1, or maybe you give a C out. I don't know why I'm here. Something like that. So we get a little verbal messaging. And now all of our warnings and errors are gone. It's showing us the current output of main. All programs begin and end with main. So it's just showing me the smallest value inside of that string from whatever question that was. So none of those little bugs were difficult to fix. But if you didn't read the error message, and warnings, I mean, I would treat warnings as errors. I would say in C++, a majority of the warnings you run into are errors in more modern languages. Both of those warnings would not compile in Java and C#. C++ will compile it and just say, oh, we're going to assume you know what you're doing. But I would treat warnings as errors, or at least go and research why it's a warning. And if you decide like, oh, okay, I understand why it's complaining, but that's not an issue for me, then you are making an educated decision that you don't have to deal with that warning. All right. So questions about any of that stuff from the midterm? Let me go and put bug fixes. All right. Let's see. There's a question on here. All right. So next step is I want to introduce something that I've previously mentioned is difficult. We're kind of rolling towards introducing objects. We're going to write our own objects. But in order to do that, we need to first learn about a couple of things that are the predecessors to objects. We're kind of walking through history, kind of what, Age of Empire style or something like that, where we're seeing this is how it was done in the old days, and then like, oh, well, this is where we hit some sort of bump in the road, and until we find a way to bypass this, we're kind of stuck in our problem solving right here. That's kind of an Age of Empires thing, right? I mean, you needed to have the siege weaponry before you can knock down the castles. If you were just out there with the bows and arrows, it's not going to fly. Tried to make a video game reference. I'm getting deer in the headlight. Is Age of Empires too old for this audience? Oh, you still play it? Oh, that's a real-time simulation of like history. It's StarCraft, but history. Civilization. Yeah, it's like Civ. Like a competitor, earlier competitor, but yeah. All right. So let's first introduce the concept of pointers. You've heard me mention this before. I said you're going to be scared by it. I promise you that it's easy, but you're still going to be scared by it. So what is a pointer? A pointer is a primitive type variable capable of holding. Now, we know about other primitive type variables. We know about ints, longs, chars, floats, booleans. So if I say int, what kind of values do ints hold? Whole numbers, right? Positive and negative whole numbers. We had a couple different categories of ints. We have shorts, we have longs. I think we saw that current C++ compiler didn't support bytes, but bytes a thing. It's definitely there in the modern languages. And really, it's just powers of 2. A byte primitive type holds plus or minus 2 to the 8th power range of values, to the 7th power, because you're using one of those bits for positive or negative. A short is 16 bits, int is 32 bits, a long is 64 bits. What's the difference? How big of a value or how small of a value it can hold. Longs can hold bigger numbers or smaller numbers if you're on the negative side than a byte. But same kinds of values. All right, so anything integer type is holding whole sign numbers. What about chars? What do chars hold? Ultimately, it's a character, but what they hold is an unsigned integer because they hold the number that maps to either the ASCII or the Unicode chart, right? But that particular type is an unsigned number because we don't need negative numbers. On the ASCII chart that C++ uses, we have 256 unique characters. Actually, original ASCII was 128, but we stored in an 8-bit value. So let's say with an 8-bit unsigned integer, we can hold 256 unique values. That is the values between 0 and 255. That's the values that it holds. And each one of those maps to something on the ASCII chart. We could go through and actually write that. Let me I'll start a new one. Practice. Oh, I had to name it. I don't want a new file. I want a new project. Dun, dun, dun. Great new project. Leave. Okay, there we go. So here, and I'll just run this real quick. Like I've always said, make sure what you have is working. It's working. So what we could do is we could have a for loop. Print I is equal to 0. I is less than 256. I plus plus. And we can do cout the char version of whatever I currently is. And let's just put a space after that. So what I'm saying here is this program will output the entire ASCII chart. If we wanted to, we can put the number before it, but let's just see it go through the whole ASCII chart. Now, what we'll probably see is we'll probably see a whole bunch of spaces in there. Because there are things on the ASCII chart, like smiley faces and playing cards and stuff like that, that this terminal down here probably doesn't know how to show. It's not capable of showing it. Oh, I need to using namespace standard. We even got some beeps there because it tried to deal with some numbers that we didn't. So there we go. Yeah, we got. We got some numbers. We got the punctuation and less than stuff. We got the uppercase letters. We got some more symbols and stuff, lowercase letters. And then a whole bunch of what the heck are you talking about stuff. We were using a different terminal that was capable of handling all the ASCII character set or all the Unicode character set. We would have the other outputs, but common thing. But the point is we just proved that under the hood, it's using ASCII. All right. If we were doing the same thing in Java or C#, we would say 65,536 there, which is 2 to the 16th power instead of 2 to the 8th power. 2 to the 16th minus 1. Okay. So chars hold unsigned integers. Booleans. Well, we think of Booleans as trues and falses, but they actually hold zeros and ones. Numbers. Everything's a number. All right. So a pointer now is a new type of primitive. Okay, but it's really an idea rather than a type. So we don't say pointer this or pointer that. A pointer is a variable capable of holding not a number, not a whole sign number between a certain range, not a whole unsigned number between a certain range, not a decimal point value, not a true or false, 0 or 1, holding a memory address. So what is a memory address? So right off the bat, let me just show you something here. I'm going to say int a is equal to 5. I'm going to do cout a. And then I'm going to do cout address of a. That's what a memory address looks like. What is that? At a glance, it just looks like a big scary thing, which is why pointers intimidate people. But what is that really? That's what it means. But what kind of value is that really? What are we actually looking at there? Something he mentioned there is this, the purpose of this is it tells us where inside of our computer's memory, we're inside of RAM, the random access memory your computer uses for real-time processing. Where in that memory does this value live? But the kind of value this is, you probably remember this. I mentioned this at some point in class, and I said that addresses, human versions of addresses are complex, yet we think of them as easy. 123 Elm Street, Mequon, Wisconsin, 53097. We have multiple components that make up our addresses. Yet we don't find those intimidating, do we? No, we've been dealing with them our whole life. Easy enough. Computer addresses look scary, but computer addresses are actually simple because everything in a computer lives on one big long street. We don't have a house number, a street name, a city, a state, country, a planet. we don't have all those individual pieces. Memory is one gigantic long street. And what is this guy? What kind of value are we looking at here? Just a big old hexadecimal number. 7FFF61F07A4. So if I took that number and we put it up here, and I said, convert that to binary, could you do it? We have the trick, don't we? Remember, with binary, we can represent the entire hexadecimal thing with 4 bits. So what's a 7? A 7 is 0, 1, 1, 1. What's an F? 1, 1, 1, 1. What's an F? 1, 1, 1, 1. What's an F? 1, 1, 1, 1. What's a 6? 0, 1, 1, 0. So on and so forth. Do this for each one of those hextets. Put all those zeros and ones together. You got a really scary binary string. We could convert that to decimal, couldn't we? Here, we'll take a shortcut here. Can I do it in here? Doesn't look like there, but there's websites that do this. So there is the decimal equivalent of that number. So this is 140 trillion, 733, 34 billion, 836 million, 508,580. Big number, but less scary. We're decimal people. This number and this number are the same number. And this number was scary enough, but it's at least shorter than this one, right? So that variable A, this guy right here, where am I at? I created a variable here. I brought it into existence. I said, C++, I want a variable named A of type integer. Go and find me a place in memory to put that. And I want to store a 5 there. Okay, so I wrote this high-level code here, and I relied on the operating system to do the heavy lifting for me. Go find a plot of land big enough to hold 32 bits, 4 bytes. That's how big an int is. So go find me a plot of land big enough to hold the thing I want to store. And it did that. So this syntax right here, putting the little ampersand before the variable name, says, don't give me the value of that variable. Show me where it's stored. Memory address is a giant number which indexes the location where a value is stored in memory. Memory is like one big long street, and a pointer is just the house number on that long street. So from a human perspective, yes, we're not comfortable using hexadecimal values all over the place, but we understand them in this class better than most would, right? If you walked up to a complete stranger and started talking to them about hexadecimal values, they might kind of wander off pretty quick. Or you're like on the Jimmy Kimmel show or something like that, where they're doing one of those man on the street things, trying to. But realistically, we could say, oh, well, we don't do hex, we do decimal values. Well, this one's not much better, right? You got to sit there and sound it out, basically, go and find, billions, trillions, quadrillions, wherever we are. We're dealing with a big, long street, and there are a lot of houses on it. So for us to have addresses and we want to keep it on one big, long street, much simpler addressing than human beings use, we're just going to need a whole bunch of numbers to index and say, well, this is house 1, 2, 3, 4, blah, 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 all the way down the line. We can look at this number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 of those. How many bits are each of those values? How many bits represent a hextet? 4. Each one of those we can represent as 4 bits. 0 to 9, A through 15, A through 15. 0 to F can be represented completely with 4 bits. So I have 48 total bits is representing my memory address in this operating system. Now, I promise you the memory manager for, this is probably running on Linux, I'm guessing, online GDB, is a 64-bit memory manager. Why are the memory addresses only 48 bits? What about the other 16 bits? Any operating system is going to have things that run as administrator, right? You've probably seen on Windows, you can right click and say run as administrator. And when you're running something as administrator or as the super user, Linux, Unix, it's the root user. It runs with elevated permissions and it runs in a special memory space where it has access to other things. So what a modern operating system like Linux does, Windows does the same thing. they're all modern operating systems, is it sets aside, in this case, a 16-bit memory space. That is a place that can hold 2 to the 16th power unique locations. And 16th power is 65,536. So that means Linux here can hold 65,536 houses in super user memory only. Whereas on the normal user running side of things, it's 48 bits. So that's 2 to the 48th power unique places in memory we can store stuff. Make sense? Where the operating system gets to decide how they're going to subdivide their memory. How small do we make the plots of land? If you have 4 gigabytes of memory and you subdivide your memory by gigabytes, you probably don't want to use an entire gigabyte as a single. You basically are having houses that are like on a bunch of acres, right? So yeah, we have 4 gigabytes, but we only have 4 addresses, 1 for each gigabyte. You're going to run out of memory in your computer real quick, right? You had plenty of RAM, okay? But somebody bought that house over there and they put like a little dog house on it and they have another 130 acres that they're working with that they're not using, that nobody else can use, because that's trespassing. Make some sense? So probably if you have 4 gigabytes of memory, your computer's probably going to break that into maybe 32-bit chunks, 4-byte chunks, maybe 8-byte chunks. You know, a usable amount of size for most tasks you're going to do. But trying to be as not wasteful as possible. Don't put a single integer inside of a gigabyte. Put a single integer, we could say maybe preferably inside of 4 bytes or 32 bits, maybe inside of 8 bytes, 64 bits. You're not wasting that much at that point, right? You're using your memory fairly carefully. And every now and then you have these larger type values like strings. We're going to be talking about structs here pretty quickly, like arrays we'll also talk about pretty quickly, which you've already been introduced to because a string is a character array, effectively. But these are things that are holding multiple values and they bridge multiple addresses inside of your computer. Remember when we walked through strings? We saw how strings are actually stored. I had 3 different little buckets. I have it somewhere up here where we had the index, we had the character, and we had the memory address. So these guys, the contents of a string and the contents of an array, which is a collection of variables of values of the same type, are sitting in contiguous memory, right next to each other in memory, where a part of the value is stored here, a part of the value is stored next door, a part of the value is stored next door to that. That's how we handle storing values that are bigger than the individual plots of land that our memory is subdivided into. And these are the decisions that the people who make our operating systems have to pick. They have to say the programs that run on this operating system are likely going to be primarily using this amount of memory at a time. So you imagine, based on the programs that you've been writing so far, what are we defining a whole bunch of? A lot of integers. Got some chars thrown in there. So integers are 32 bits. And we're probably working with integers more than anything else, right? So basically, if we had our memory always handling 32 bits, we're going to cover basically everything, right? 95% of all the stuff we do will fit nice and cozy inside of 32 bits. If we stretch it to 64 bits, that allows us to hold some bigger integers. And yeah, things aren't packed in quite as tight, but we're not wasting that much space. Every 2 integers counts as 1 memory location, but we couldn't store 2 integers there. We can only store 1, but it allows us to support longs. But the operating system designers made that decision. They decided, hey, this is how we're going to subdivide up memory. This is the smallest chunk of memory the user can use at a time. The operating system handles the heavy lifting. Your program talks to the memory manager of the operating system. It just walks up and says, look, I got a value. I need you to put this somewhere. The operating system goes and does it. We're just talking about what's actually happening behind the scenes. Kind of like visiting, the Amazon warehouse, how they learning about how they store stuff behind the scenes. They got all these robots that zip around with, did I tell you about one of those? I visited one of those down in Pleasant Prairie. It's like 45 minutes from here. It's a free tour. Fascinating. I encourage everybody to do one of the Amazon tours. It takes you through the process of when you do one of those, buy it now and it delivers it today. Like what that whole circular process is from when you hit that buy button. And it's really fascinating from a computer science perspective because you're seeing humans and robots and AI all working together. Where when you watch it, the human beings are kind of the joints. They're taking one process that was handled by robots and handing it off to another process that was being run by robots. And like when they're putting something to store, pack away, like in memory type thing, the correct cart pulls up on a robotic little, I don't know, car or cart thing, and a light flashes onto the cubby hole where they should put the item they were supposed to put away. So a human being scans an item that they're supposed to put away, or they're supposed to ship, depending on which direction it's going. They scan it, a cart zips in with a light pointing on it, they put it where the light is. You wouldn't want to do that job more than like a 45 minutes at a clip. You start going crazy. And then what they do is they gamify it. So most of their stations have like a video game associated with it where you're actually competing against the productivity of other folks. It really is kind of fascinating. You can demonize Microsoft and Amazon or whatever. All these big companies are mean and nasty and stealing money, whatever. We need them. So you might as well go and see how their processes work. So I'd encourage, it's really, really fascinating. And it's free. Okay. So, like I said, no homework for Tuesday. I will get caught up on okay, well, I promise your exams will be done before Tuesday. I expect them to be done sometime late this afternoon. All right, so keep an eye open because what happens is I grade the exams one question at a time for the entire class with the names off. So most of your exams are 80% graded already, but it doesn't release the answer until I have all of them 100% graded. So I only have 2 questions left for everyone. So I guess I have like 85, 90 questions across 2 sections. All right. Well, have a good Friday. Have a good weekend. If some of your parents are coming in, this is like homecoming weekend or something like that. Have fun with that. Take the nice break from coding. Good hard work this last couple of weeks. Give me 1 second.